So today we're going to talk about linear algebra using basically computer, using numerical methods, all right? So the same technique that we kind of went through, we'll add few more, all right? And we'll see how they are being used in on the computer, and you will have computer programs on Desire to Learn that basically you will solve the same problem 3 times. You will solve it manually, and then you will solve it basically using 2 numerical techniques, right? So solving those linear system hive equation direct can basically be generally divided into solving it directly or solving it iteratively. This Gauss elimination method, getting the inverse, Kramer method that we went through, remember the determinant, and saying x of I is di over d, and all those are direct method. All those give you, here is x1, here is x2, here is x3. So today we will see another category called, number 3, it's called solution by iteration. So similar to Newton-Raphson and similar to a fixed point iteration, all those things that you have initial guess, you keep trying and trying and trying until the number kind of stop changing, that we will do for a big system of equation. All right? And you may wonder, right now, some of you should ask me, what is a good question right now? A good question would be, why solving it iteratively if it's linear system? I mean, we understand why you do this on a nonlinear equation. Huh? Sine x over e to the power x, yeah, we have to iterate, but x1 plus x5 equals 7 and x1 minus x5 equals 3. You have to iterate on something like this? Amazingly, it will take less time. It could, for special matrices, it could take less time than the direct method. Alright, so that's why you would use it. Not because you want to keep just iterating, but because it may take less time on the computer. Alright, for a big system and special kind of matrices that we will go through, it actually pays to iterate on them. Alright, so the first method, we already know Gauss elimination, right? What's our job when we are trying to solve ax equal b? We do this by turning a into, you remember? Upper triangular matrix or lower triangular matrix, any way to basically have at the end one equation, one unknown, solve it, and then back substitution all the way till the end. Alright? That's what Gauss elimination was. So you look to a matrix, of course you work on the accumulated matrix when you do it by hand. So you include basically the A and the B. Right? And your job is to turn this into upper triangular matrix. Everything else is 0. Right? So the computer and you should also start that step. Both of you should basically say, this doesn't work here, right? Why doesn't work? Why cannot start getting zeros under? Right, because the first one is 0. So because of this, you should basically look at those things and say, well, where is the biggest number? So 6 is bigger than 0, I'll put it up there. Of course, if all of them are 0, that's something else. But you look for the biggest number and you basically exchange those rows. Right? So you'll see this in the computer program in a second. And once we arrange them, then it's perfect. We will use this to 0 under it. Okay, so we need a multiplier for the second row. We need a number that we multiply the first row with so that it can get 0 under it. Alright, and multiplier for the third row. And every row underneath it has this multiplier, and that multiplier will always be this guy and this guy, right? And a negative sign. It's basically this divided by this, and then you multiply it by -1, and you multiply by the whole row over here, and you add it. Right? So you don't guess. It's simply just minus this a divided by that a, and let's multiply everything here and add them. You are guaranteed to get 0. Of course, if you get 0, 0, 0, 0, then if one equation vanishes from you, then you know that the system now will have more unknown than more equation. That's obviously what? Unique solution no solution or multiple solution. If you have one equation vanishing from you, 0, 0, 0 equals 0. Not only did you manage to get 0 over here, but you get 0 and 0 and 0. No, that's infinite solution. That's basically three unknown, but now only 2 equation. It's like 2 unknown in 1 equation. x1 plus x5, x1 plus x2 equals 7. How many solution? Infinite solution. Just pick any x1, you get x2 for it. All right. So I'm not going to repeat this, although this may show up in the quiz next week or it's not in the homework, but basically it's simply he's using this pivot to cancel underneath, right? And since it's already here 0, the computer code or you will basically say, even if you don't know, you will basically say, well, it's this guy divided by this. Well, 0 over 6, that's 0. So you know that you multiply this by 0 and you add it by this. Basically, you don't do anything because there's already 0 there. Your job is done. Right? You go to the next step and he look to this, and he basically, before he actually do the zeroing, it helps if the matrix is diagonally dominated, if the big guys are at the diagonals. Right? That's also for iterative method. It really helps if the diagonals are the big numbers. It makes the solution converge even for iterative method. So you look over here and he basically decide that I'm not gonna use this to zero this, I'm gonna use this to zero this. I'm gonna change these 2 lines. So he immediately changed 8 was 4. And then now let's use this to 0. This work just in case even this number end up being 0. You always have the same rule. It's basically before I start zeroing, I have to be a little bit picky on what is my pivot. My pivot should be the biggest number available to me. All right? And so mission accomplished, upper diagonal matrix, right? And this last one, that's the solution for the last variable, right? x3 basically is this over this. x3 is minus 3 over 2 over minus 3. Become half. And back substitution take you all the way up. Okay? And so here is not really the computer program, but the algorithm. Again, it needs translation into MATLAB or Excel, Visual Basic, or whatever the language you're writing on. Right? And you can see basically here he's scanning. He's going through the first column, and then he's going under it for the different rows underneath, scanning which one is bigger, and the one that's bigger he's picking it, right? And if it's not bigger, then he's changing the rows. Of course, here in that algorithm you can say else exchange row K and row M, but in the MATLAB you basically have to say, well, X, all this, you put it in a box or storage, temporary storage, and then you pick X new as basically the previous from the next row, and then you take the storage, the variable from the storage, and bring them again. It's take basically a little bit more work, right? Take more work to actually do this. And then see, here is the multiplier. See, it's AJK over AKK. Can you see from far away? You had it printed, all right? Good job. So AJK over AKK. That's the multiplier, and then here is the minus sign. See, the minus sign is here. So he go and every single one of them, and he used the multiplier on the row, the top row, and basically change those numbers. By the time he's finished with all the rows, you have upper diagonal matrix. He start with the last one, xn. Right? And after he finish xn, he finished the rest of them. He go all the way up. He's starting from, he finish xn here, and over here it's n minus 1, n minus 2, n all the way to 1. Alright? So again, we will not talk about how do you do those loop very efficiently, but you will basically, in one of the homework problem, you have the program, and basically I'm asking you which method did he use. So you will look at the formula in the file, and you look at the formula over here, and you basically say, is it a matching? Then it must have been Gauss elimination. If it doesn't look like it, then it's not Gauss elimination, it's something else. You look at the other, there's an algorithm for each one of them. Is that easy? Right? You just watch the formula and try to see if it's the one that's described here or not. Alright. So this method, you can guess it's probably taking a lot of steps, right? So they actually figure out that they can save on the number of steps by making it a little bit different. And in case you are thinking, well, what's the big deal? My computer is really fast and I can. No, when the system get bigger and bigger, when you have so many equations, it takes few minutes. And when you want to do things that are basically on real time, you are observing a target moving, or you are tracking a person coming into the room, and the code basically are trying to solve the equation so that he can turn his face or see something. It really pays to, are we doing it in 10 minutes or 1 second? So it's a big deal to get the solution in real time. So it's not like, I can do, what's 5 minutes between friends? No, it's a big deal when it's 5 minutes. Alright? So this method, and this is what you're going to do in the homework by hand. Alright? He basically said, we are solving x equal b, right? But we will turn this A into two matrices, lower and upper matrix. Okay, that's where most of the time is spent when you're doing it by hand, to turn the A into lower and upper matrix. So let's imagine we have this matrix 2, 3, 5, 8, and 5 can be turned into those two guys. How? We will see next. You will see how it's being done. But let's just imagine that A, we know the procedure to turn into two matrices. So now what? Now imagine you're going to put those two guys in here instead of the A. So you have lower multiplied by upper multiplied by x equal b. All I did was just changing the A into the two guys that represent A. Can you see now? How's that going to help? Remember what happened in Gauss elimination? What was our job in Gauss elimination? This first step was turn it into an upper triangular matrix, because we can run the back substitution very quickly. Can anyone invent this method for me? The guy who invented this is called Doolittle. So can anyone think like him and figure out how do you solve x? Exactly, that's the job. How to solve for x? Easy. No, then that's basically the inverse method. No. Again, he was looking at the Gauss elimination and thinking that's ideal. If everything is only upper triangular matrix or lower triangular matrix, I can just run the back substitution, get the solution immediately. I don't have to do it. The back substitution step is just a formula, right? Look at this. It's just a loop of let's multiply and get the MATLAB will do this like this. So is there any hope we can use the back substitution right now? I'll give you a hint. 2 back substitution is all we need right now to get the solution. How is that possible? With 2 back substitution steps, you can get the solution for x.
Because the 1 is the solution in the lower. It's -7 is the solution in the upper. So
Don't forget about number. Don't look at the number. Just look at this formula. Look at this formula, because I mean this. What are you saying?
like there's only 2 rows.
No, let's imagine you have 100 rows. 100 and 100. 100 lower, 100 upper. 2 matrices, one of them is lower, one of them is upper. By lower and upper, I mean there's only numbers on the diagonal and yeah. So I imagine 100 by 100, but this one is upper and this one is lower. And they are here next to x. How can I use the back substitution to get x? Anyone for a free homework? If you answer this, you don't have to do the homework. Last call. You turn this into y. You call this y. Y, I don't know. I didn't know x, I don't know, of course, y. Y is u times x. So if I don't know x, then I don't know y, right? But look what happened now. By calling this y, now Ly equal b. Can you do back substitution in this? Yes. Why? Because it's a lower triangular matrix. There is a back substitution for it. You get the solution. And then what happened after that? We know why. Well, you know why. Remember x is y. Except y is known now. Can you do back substitution? Yes, and you get x. So basically, once you have two lower and upper matrices, all you need to do next is two back substitution, and those are very quick formulas to be done. So it turned out this is actually more efficient than the Gauss. It saves on the time of the computer. All right, questions? So now your question should be, well, but how you do the decomposition, right? So that's what we will see right now. So the do little method, it's basically about turning the A into lower and upper matrices, and then calling the y, or calling ux as y, put it on the side, okay, and solve for the y. And once you solve the y, you go back again to your definition. What did you say? Y is ux. Okay, now you can solve for the x. Okay, so here is the, I guess, the same problem. He's solving it with do little method. So the one that we are solving in the homework is this. So this is basically coming from an electric circuit. So you can imagine if that electric circuit is actually much bigger, you will generate huge number of equations. How do we come up with those equations? Every node, what happened at the node? You remember from me?
Goes out.
Right, exactly. And that's what you see over here. Minus I1, the current one, plus I2, plus I3 equals 0. Okay, I1, I2, and I3. So he's looking at I2 and I3. They are coming at this point, and they are leaving over here. So minus I1 plus I2 plus I3 equals 0. And then you have, so every node, what come in, got come out. And then the voltage over the loop. Remember? IR. So 4 times, where is 4? Here is the 4 times I1. 4 times I1, 12 I2 equal the 12 voltage and 24 voltage. And the third loop is over here. So at the end of the day, sorry, at the end of the day, here is a system of linear equation, right? And it can get really huge depending on how many nodes and how many loops you have. So basically said, use that do little method to solve for those guys. So once you put your hand on the eye, and surprisingly some students in the exam, their problem is to look at this. Some people actually have a problem looking at this and turning it into A times X equal B. Why? Because not every equation have I1, I2, and I3. So some of those guys will end up being 0 in the matrix, right? And also sometimes it confuses them that if they are not in order, like if the equation have, you know, like this one said actually 12 I2 plus 4 I1 equal 2. They will end up putting 12 at the beginning. No, it's the number next to I1 is the one that should go first. So I want you to practice basically, or make sure that you know how to look at an equation and put them in a matrix. That's the first step. Second step is to do that transformation, right? I guess there is a middle step, which is if you don't like the 0 at the beginning, you basically exchange the rows with the column. So it's not 0, 3, and 6. No, it's 3, 0, and 6. So basically he took the whole row here and you put it here. So 3, 5, and 2. Okay? So now we actually have, we will end up having 6 equations coming up from those 9 equations coming up from those guys. So we cannot really afford to have more than 9 unknown. Each one of those numbers will give us 1 equation. So the lower and the upper matrices that we have, let me clear this. Here's the lower, here's the upper. We cannot just have 6 variable over here and 6 variable over here. That's just too much. We can only have 6 and 3. That make 9. We don't have the degree freedom. We don't need it to. So the diagonal, we will just make them 1, 1, 1 on the lower matrix. Okay, if you make this m and m and m, then you have just 2 more unknown than equations. So why we have 9 only equation? Because each one of those numbers, this 3, 5, 2, can give us an equation. Where this equation is coming from? Where is it coming from? Let's start with like this 3 guy. Why this will give me an equation? Because where did this 3 come from? It's lower times upper. I have to multiply this times this to come up with that 3. So here is an equation. So each one of those guys will coming from the multiplication of a row and a column. So it's this row and column, row and column, row and column that will give you 9 equation. And now you should think, that's horrible. You get 9 equation in 9 unknown, and how is that gonna help me? We were had 3 equations, 3 unknown, and we were trying to solve it. Now we have 9 equation, 9 unknown. No, it's every equation actually is not an equation. It's just a formula to give you one of the variables. So if you do them in that order, so I mean 3 and then 5 and then 2, 0, 8, 2, every time you write it, you hit one of those guys. Okay, we'll see that in a second. So here is the 3 again. So that 3 is basically this times this. He's doing it over here. The 3 is coming from this first row times this first column. So because of the 0 and the 0 and the 0, the only thing is 1 times u1, 1. You actually have u1, 1. Alright? So you are done with this. Out of the 3. Let me put it in green so that makes sense. You are done with u1, 1. And then the 5, when you do the 5, let's do it in different color. So where this 5 is coming from? So basically the first row, second column. So you will end up basically, when you multiply this by this, you will end up getting u1, a2. So you get this guy. And consequently, when you do this guy, you will get this guy. And you start here again, and you will get this guy. And then this, you will get this guy. And then this, you will get this guy. And so it basically just, every time you use one of them, you will hit one element from here and one element from there. Alright? So it's not like equation, it's really just formulas to come up with those numbers. Right? So if you just follow this order in your notes, you will see basically how he's gonna get those and those in that order. So basically here you get this, and then he will get this, and then this, and this, and then this guy, and then this guy. Right? See how he's getting the M31, and then the M, so M31, and then the M32, and then after that the U33. Right? Just basically that order. Is that clear? Rows, 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 rows after row.
So you do
row by row. Right. And so he end up with, here is his lower and here is upper. And again, the lower matrix had 1, 1, 1, 1 by choice. I mean, we picked those numbers to be 1. And so now he would basically say, now we know A, x equal B, and I just split this A into lower and upper, x equal B, I'm going to pick this middle guy here, and I'm going to call them y. That leave Ly equal b. So he will take this lower matrix, and here is L multiplied by y equal his b. Remember the b we split, we end up changing the 8 and 7, the row with the row. So he's now solving for y by back substitution, and it really helped too because this is not just any lower trigonometric, it also has ones on it. So I guess basically y1 is already 8, right? It helped that this guy comes 0, sometimes it's not 0, so that would be 2 equation, 2 unknown, but that's okay. And you get y2, and then you get y3.
And 5 of your numbers in that upper equation, in your upper triangle are all the same, they only change the bottom number from an 8 to a 6.
Say that again. Those guys are all 1, the diagonals are all 1, right?
Right. What I'm saying is from your original matrix, your upper triangle stayed the same except for the bottom corner, which
correct.
is 6.
Right. So now, after you're done with your y, you remember what you did. Your y is, what is this mean unknown? It's u times x. The upper times x. So he take his upper that he just turned it, this 352, and he put it here. This upper is upper times x equal the y that he just came up with. That's the y he just came up with. And you solve for x. Again, lower upper diagonal matrix, back substitution, you get 6 and 3, you solve for x3, and then you solve for x2, and then you solve 1. You solve from the bottom all the way up. So you will do this by hand at home. Alright? And then he basically said use the solve problem 2 using MATLAB file on desire to learn notes that you have to modify the matrices in the file to match the problem you are solving. Print the corrected file and the solution. So there is a do little program, and the matrix almost look like this, although I missed a few lines. In the coefficient, put 1 0 here, deleted number. So you just go to those lines and fix the number to be exactly the matrix that you're trying to solve. And so that helps. The solution that you should get is basically the solution that you did by hand. And that also illustrates a very important point, that when you write a very complicated computer program in the future, verification is very important. You need at least to check on him. You shouldn't trust it just because the pictures are so pretty and the program is so long. How could it be wrong? Of course it's wrong. Right? Then you basically have to do one calculation or something that's very important. There is no question what is the answer, whether you do it by hand or whether you are giving him a dummy problem that you know exactly what it should do. Okay? And then you basically compare the results to him. So running this basically, it's kind of, how the program is written, but also it helps you to validate the numerical results that you did by hand. It also helps you to validate the program and see if there's any mistake in it. Questions? All right. So that turning or decomposition of the matrix into lower and upper was done by basically the help of those factors, those numbers on the A matrix, right? That's what we did. So each one of those guys, when you think about it, actually can be generalized. And so this is basically the program. The program is simply those 4 lines and 2 back substitution after that. So this is basically how to come up with UGK and MGK. Right? So in the program you will see how he's basically doing that summation. He starts by zeroing the box where he's adding stuff, and then he basically this just become a for loop. He loop over this guy from this number to this number. Alright? Questions? Very good. So now if the matrix A that we want to solve or use it to solve for x, you are lucky that it happened that it's also symmetric, positive definite, meaning that, look at this, 2 and 2, 14 and 14, minus 5 and minus 5. Then it turned out that not only you can just turn it into any lower and upper matrix, any matrix can turn it into lower and upper, but you can also turn it into lower and the lower transpose. Alright? So why is that helpful for us? So basically,
Makes it a lot easier to use
right,
one and then turn it.
right. So basically it's, you don't have that many number of unknown. So basically here it is. So here is this is symmetric or not? 2 and 2, 14 and 14, minus 5 and minus 5. Yeah, that works. So this is basically not Doolittle. This is called basically Cholesky method. And what he did was, well, I'm gonna put L11, L22, L33, L21, L31, L32. But over here, I'm gonna also turn the rows into turn the column into rows. So you see the same variable again. So L11, L11, L21, L21, L31, L31. Right? So, and he's basically doing it again line by line, except you go faster now because you have only 6 unknown. And once you turn it into those two guys, it's the two same steps again. So basically, lower time I equal b, and once you get the y, then ux equal y. Right? And again, the u is not in u, just the lower transpose. And you solve for x and the y. Alright? Questions?
Not until I tried it.
Alright. So the formula is here, and so this is supposed to actually to run a little bit faster. And you can see this is again the computer code or the algorithmic thread. So if the homework was basically in the third problem, you were given the program and said, well, what method is doing it? You look at those formulas and you look at the other one and you compare them and you would say, well, is it Doolittle or is it Cholesky? Right? Very good. The Gauss-Jordan elimination, that's basically when, remember, he was not just doing upper triangular matrix, he ended up doing it, turning it into just an identity matrix, into 1, 1, 1, 1, 1, and zeros everywhere. Why? Because on the other side, he was doing the a minus 1. So then once you have a minus 1, the solution is simply a minus 1 times b. So I'm not going to talk too much about it because it takes, first to start, MATLAB can give you the inverse by just one command. You'd say inverse a and he'll give you the inverse. And also because I want to switch to now iterative method. So what's the point behind this iterative method? First, you'll be surprised how many software in the market actually use iterative solution, not direct solution. Alright? So the idea came from this. Look at this system. This is 4 equation in 4 unknown, right? But then they look at those equation and someone thought that, well, those are not equation. Those are actually formulae to calculate x1, x2, and x3, and x4. I can turn this equation into, let's put x1 on one side, put everything else on the other side. This equation, I can put x2 on one side, put everything else, send everything else to the other side. And now those equations are turned into, here is how you calculate x1, here is how you calculate x2, here is how you calculate x3, here is how you calculate x4. The only problem, of course, is that it's written in terms of the other guys. But if you have a good guess, what are the other guys? What's x2 and x3 and x4 and x1 actually? If you know kind of roughly where they are, maybe this will work. Maybe you will calculate them very closely. And if you are not close, well, at least you made the progress. You made the guess a little bit better. We'll try again and try again and try again. You keep trying until the x's that you are using is the x's you are calculating. The x old are the same as the x new, or close by, or the difference between them is less than your margin of error. You are happy. You know the difference is 4 digits. They are almost the same. We are good. We are done. So that's what the iterative method is, right? So when would this actually pays and make it, because the iteration takes a lot of time, right, to converge. It pays if those formulas are short. They are like really very concise. Why would the formula be short? Say you have 1,000 equation and 1,000 unknown. If you have 1,000 equation, 1,000 unknown, it takes a lot of time for direct method to solve the solution. Gauss, Doolittle, Cholesky, all those guys will take a little bit more steps to come up with a solution. But the same 1,000 equation, 1,000 unknown may be much faster here if the 1,000 equation, 1,000 unknown, every one of those equations have only 3 unknown. I mean, the system as a whole, yes, 1,000 and 1,000, but the first equation is like this, the second equation like this, the third is like this, the fourth is like this, the fifth is x3, x4 and x5, the next one is 5, 6 and 7, the next one is 8, 9 and 10. This happened a lot in CFD, computational fluid dynamics and heat transfer problem, and all those basically, when they take the domain, the car or the engine, and split it into small points, every point is usually connected. Right. Exactly. Everyone is connected only with their neighborhood. So yes, at the end of the day, you are solving for 1,000 points along this engine or inside this room to find the temperature, but each one is just connected with the guy next to it. Each equation has only, say, 5 unknown. So the iterative method will fly through a system like this. So this is called, when the matrix is like this, full with zeros, except for maybe 5 diagonals, and the rest are zeros. But there is just like 5 full diagonal, 5, or I'm not saying 5 exactly, but it happened to be 5 in CFD. But if the matrix is kind of like full with zeros, except for few guys, that's a sparse matrix. That sparse matrix is very friendly to an iterative method, right? So basically that's how those things work. You are simply basically saying, well, what's the initial value, and you calculate the new value out of them, and you just keep iterating over and over and over. So here's an example. So I guess we are doing this, right? So out of those formulas over here, he's basically, so this is the not really, let's call it I. This is the number of iteration. And you can see as he basically iterating, every one of those lines. By the way, in Excel, how does this look like in Excel? Piece of cake. It's simply, each one of those guys, he's bringing the old value. So let's imagine this is the initial guess. So this is basically calculated based on this equation. 0.25x2 plus 0.25x3 plus 50. So this is 0.25x2 plus 0.25x3 plus 50. You calculate this, right? And this x2, look at this equation. x2 is 0.25x1 plus 0.25x2 plus 50. So this is 0.52x1 plus 0.52x4 plus 50. And so each row is basically calling, well, each element is calling the previous value of his constituency, basically the guys that are building him, x1 and x4, x2 and x3. And so once you build that formula, you take that thing and you copy it through the rest. That's the program over Excel. Alright? So that's when you go to compressible method, and you have bunch of equation in bunch of unknown basically, and you want to solve them iteratively, all you have to do is basically on Excel, each one is basically calling the value that he depend on, 0.5 of my Mach number plus 0.7 of the pressure plus whatever, and that's it. Once you made the cell for each one of them, you just copy it and they keep updating themselves.
Where did the first set of numbers come from?
Right, excellent question. So the first is your initial guess, and the commercial software, you know, for fluid mechanics, for example, they give you the option what you want to specify initially. They have no idea what you want, what is the initial value. Of course, the closer you are, the less time you need to converge, right? So you are given, commercially, you are given that option, basically to say, well, I think the temperature everywhere is T ambient, or I think the velocity everywhere is 0, there is nothing moving, or I'm just going to assume the uniform velocity throughout the whole thing, right? So in the exam, you know, probably I should give you the initial guess so that you wouldn't suffer. But in the homeworks, you can suffer because it doesn't cost that much to basically let Excel try over and over and over, right? Right. So how do they? So basically, he's keep repeating it until, look at this. The numbers kind of x4 very close, x3 very close, and x5 is. So if he is looking for 3 significant digits, he should be happy, right? Yeah, but you track the weakest link. So within 3 digits, basically, he is happy, so he stopped. But if you want 4 digits, he would go further, right? So that's basically a solution. But then, commercially, the program basically, like Fluent, for example, doing, again, fluid mechanics problems, he asks you, or he gives you the option to tell him how strict he is in tracking that solution, because he solves the problem iteratively. So all that flow around airplane or inside pipelines, he cannot afford to solve them with a direct method. He has to iterate, right? So how does he iterate? Well, use one version of those guide, not exactly this one, a little bit modified version. We'll see them in a second. But it's iterating, and he need to basically say when to stop, right? So this is basically given over there commercially in terms of the residual. He basically give you how small should the residual be. What's the residual? Well, remember, we are solving x equal b. Huh?
When he plugs it in for x, but left over the
Well, so now right, so that x, he have a wiggly thing on top of it. That is the solution after I iteration. Huh? He did 1,000 iteration. He ended up with those guys. Are those the solution? No, but they are close. The solution is the x that we are trying to get, but we end up getting the x prime. So, you know, if I ask you what is b minus ax, you should tell me it is 0. Why? Because remember, we are solving ax equal b. That's what we are solving, ax equal b. So b minus ax should be 0. But b minus a, that x was the wiggly thing, x Matilda thing, is it 0? You hope, right? You hope it's 0, but it's not. It is actually a number. That number is small. That number, we call it r. That number is a residual. That's what the software will tell you how small you want the r is. Because after they come up with a solution, they plug it in the equation, they get the residual, and then they say, did we make it? Is b minus ax wiggly thing is 0 or not?
So it's the amount of error, basically.
Right, it's basically how small the error is. And so, of course, then you see it by default, they are putting it 001, for example, in the software that I'm using. If they get within 001, they are happy. But you want it to be more accurate. Then you say, no, I wanted 00001. Let me add 2 more 0 from me.
Should you do a plus or minus for that?
So right. This is basically the It's not the plus or minus, it's the absolute value, correct. It doesn't matter whether you are more or smaller.
Yeah, but
It's
some of these went negative, so.
right.
we
It's
wanna
the
look at that
magnitude,
too.
correct. Correct. It's the magnitude.
So should you put absolute value sign around the R?
So the R is calculated basically as there is a bound on the absolute value of R, not the plus or minus. So if R is minus 0.01, that's not acceptable. It has to be minus 0.00001 if you put that limit on it. Right. They are not checking whether it's plus or minus, it's the absolute value of it. It needs to be smaller than this. Alright? So hence R is small if X has very high accuracy, of course. So you would expect that if X is pretty good, then R should be very small. Right? Well, sometime we will learn today that sometime the R is really small, although the X is really bad. That's really unlucky. It doesn't happen for most systems. But there are certain systems called air conditioned that they are very tricky. When you try this R and it's pretty cool, it's very small, you think, wow, we are there. But no, you are not there. That's not the solution. It's kind of like any X will do basically. Meaning any X will give you a small R. But is the X a solution? No. How is that possible? It gives you very small R. You should be happy. No, but it's kind of the system is such that anything will do. You know, if the solution, let's say the solution is 5, but if you try 50, it will still give you a very small R. So should you design your system to handle 50 kilogram? No, it actually should be 5. That's how the solution is. We'll see why in a second. But anyway, so I explained to you how the Excel do the job, right? It's much really easier on Excel than in MATLAB or Visual Basic, because all you have to do is just basically the cell bringing their older value and you just copy the formula, right? Here it's a little bit longer because you have to see that turning this into this, it's basically you are saying the diagonal element equal everything else divided by the coefficient over here, right? That's what this formula is. So the formula has this summation that you don't see it on Excel. It's basically, that's what this, alright? So it should be 1 over IJJ. We understand this part. Y is dividing by the coefficient because it was AJJXJ equal B minus everything else, right? So why there are two summation, not just one? So the summation from 1 all the way to say n, where k not equal to j, because you don't want to add himself. That would be the method that we just explained in right now. By the way, it was called Gauss method. So Gauss-Seidel method, that's a little bit I'll take this back. The previous method was called Jacobi. It's like the straightforward method. This is a little bit more improved by doing this summation into 2 parts. Why do you think he's doing the summation in 2 parts? Let's go back again here. Can anyone improve what I just explained and get a free homework problem? What did I say? I just said you take those equations, you turn them into formulas, alright? And then where do we get those values? That's the initial guess. And we use them to calculate the new value. And we repeat ourselves over and over and over until the numbers settle down. Do you see any room for improvement in this method? Can any one of you invent the Gauss-Seidel method for me? And you have a free homework problem. So in your homework, the next homework, you just on the piece of paper you basically write on this problem free homework problem, right? You pick any problem and you don't solve it, you get the full mark for it. All right. So what was your name again?
Brian.
So what Brian said is that use the new values. Why you keep using the old values? Like this set, I understand when you are calculating x1 you are using x2 and x3, the old one. But when it comes to here, why you keep using the old x1? You just calculated a new one right now. Huh? You just calculate the new one. Shouldn't you take advantage of this and use the new x1? Of course, when it comes to x4, you have no choice. You just have to use the old one. We didn't calculate the new one yet. You have to use the guess. And again, when it comes here to, for example, x4, we'll use the new x. So up, now imagine 1,000 equation, 1,000 unknown. And we are calculating x50.
You should definitely shorten your iterations because you're getting that much closer every single
Exactly.
time.
Exactly. So when you are calculating x50 from 1 to x49, use the new one, and from x51 to x whatever, huh? Use the old one because you don't have a new value for them. So basically in Gauss-Seidel method, he's taking advantage of this by, so the power that you see, kind of the power that you see in that algorithm. Of course, in the program there is no power. You cannot write x to power m. You basically call it x new and x old, for example. Huh? So he is basically up to using, notice that he's doing j. Up to j minus 1, he's using the new method, the new values. And the old one, we keep them for basically the x j plus 1 all the way to xn. Right? So he's always updating the calculation. Right? So that's exactly the last part of the homework. The last homework problem. He said problem 2 can be solved using iterative method. Use the MATLAB file on desire to learn can solve this equation employing an iterative scheme. Use it, and then he said which iterative method was used in the MATLAB file. So I want you to look at that MATLAB file and basically tell me, is it this or is it the one without updating? It's actually Jacobi. It's called Jacobi method. So the Jacobi method is the one that without basically iteration. Sorry, without updating. See the Gauss-Seidel. Yes, the Gauss-Seidel is the one that correct the variable all the time. Right? It's this. This is the Gauss-Seidel method. The Jacobi method, huh? It's the one without iteration. Sorry, without updating. He just used old number all the time until he moved to the next iteration. Okay? So how it would look like? How would the Jacobi method would look like in here? The one that doesn't have iteration. Sorry, doesn't have updating. This formula will just be missing the n plus 1. Then it just become k equal 1 all the way to n without, of course, the j part. You have to skip the j. It's basically as if this will end up being m. So he's adding all the old value. He never used the new value for his calculation. Row after row after row after row, he's always using the old values. Okay? You might think that's really a bad idea.
So you'd actually take off as the plus 1 there?
Right. But when you say it like this, it's done by basically changing the loop in the program. It's basically, you will see he's always using x old, not some x new and some x old. Right? That's what it takes. By the way, what is that step? Look at this. You see this, guys? If the maximum xjm plus 1 minus xjm less than epsilon times xjm plus 1, then output xm plus 1 and stop. What's that?
Is it
Right, he's checking if he hit the target or not. But it's not really residual, it's the difference between two successive iteration. If the two successive iteration basically are very close to each other, he's calculating almost the same number, then he will stop. Right? So this
You could actually put an R there and tell it, up to this close.
yeah, you can. So you add one more line and you check on, you calculate the R by saying B minus AX. Alright? But see how close, how small this program is compared to the Gauss elimination or the, alright? Question so far? So the homework is to look at this formula in the program that's already written and figure, is he splitting the summation into new ones and old one? Then it's Gauss-Seidel. Or he's just using all the old value. Then it's Jacobi method. Or there's the third method, and that could also be there in the program. So this is back on the Jacobi. Why would anyone make the Jacobi method? Is it useful at all to keep using the old one? Let's see why it sometimes, not only people use Jacobi method, they even use kind of like super Jacobi method, meaning they slow the program even more. They slow the iteration, they don't want to go to the solution, kind of. Imagine that.
Plot points to smooth out your graph.
Well, let me first tell you that story, then I will answer. So there was this mathematician, and he was hunting duck. This is my impression of a duck. Okay, imagine this is the duck. Okay, and so he was shooting on the duck. All right, and he realized that it really pays off if he doesn't shoot on the duck. If he shoots in front of the duck. So by the time, and so he was working with Gauss, with Jacobi method in some of his calculation, and he actually in Gauss-Seidel. He was working with Gauss-Seidel, and so what? What's the relation between the duck and Gauss-Seidel? What do we do in Gauss-Seidel? Let's say I'm plotting here for you x1. I mean here x1. And so x1 in the first, this is the x naught, or the iteration I0, that's the initial guess. We started with 0. And then this is basically, I'm plotting here the number of iteration. And so at 1 he end up with this, at 2 he end up with this, at 3 he end up with this. Do you see what's going on? Do you see how the difference is getting smaller and smaller until what happened eventually? You don't get any addition, and you're done. The calculation, basically you put the number, you get the same number. This graph, there's another graph for x2, another graph for x3, another graph for x4, right? Each one of those numbers are, you are building the. So now I would like one of you to invent the method that he invented after coming from his hunting season. He doesn't shoot at the duck, he shoots ahead of the duck. So, how is that helpful in solving iteratively bunch of equations? Huh? Exactly. So where do you want to hit the solution? You want to hit the solution on the solution or ahead of it?
Overshoot it.
Exactly. So basically, if this iteration between 1 and 2 is telling you that x1 is adding 0.3, it was 1.7, and now let's add 0.2. So it was 1.7, okay, and we are adding 0.2. So it's supposed to be 1.9, right? It was 1, let's call this 1.7, and then this small difference here is 0.2. Should you accept 0.2? Or you say, well, let's make it 0.3.
Yeah.
Let's put it a little bit forward, because I know that eventually he's going in that direction.
Mm-hmm.
So that's the trick. If the duck was actually doing this,
Is it kind of like what we were saying before class on the homework? Like when you said, yeah, if you look at the test, you could know, like, oh, it's, you could go a little further instead of using the x in for the next x in plus 1. You can just guess a little more.
Almost
Try to get there
right,
faster.
but the trick is that you need to have this behavior. The root or the solution should basically going into one direction. They are not jumping up and down. Right? When I was young, I was a member of the shooting club, and people would shoot on pigeons. So the pigeons are sitting on chambers under the ground, and the chamber basically just push them up. And so there was this one pigeon, and the guy basically, so the guy having the gun, and he gave the order to the machine, and so the machine basically kicked the pigeon up, and then the pigeon came. He has only 2 shots, so he fired on it, and then the pigeon basically didn't like it. She went back again to the hole. She decided, no, I'm not gonna fly today. That's really very bad. So that's not a good target, you can. But if you basically, if the pigeon keep flying in the same direction, you know where to shoot, to aim basically. So what I'm saying is that this method work if the solution is increasing in the same direction ahead of you, right? So they call it successive over relaxation method. SOR stands for successive over relaxation method. Alright, we'll see the formula right now, how you can add a little bit extra on the solution. But right now, let me tell you that if the solution, and that happened a lot in fluid mechanics, if the solution start going up and down, like this pigeon that went back down,
This doesn't work.
it's horrible if you actually say, I don't want to go there, I want to go even more here. Right? Oops, right? And then here you will get this solution, you say, I don't want this guy, I want to go even more. So what will happen in a oscillating solution like this is that you will end up push it even bigger and bigger. You will actually make it diverge. So what would help in a situation like this?
Plotting it, graphing.
No. Go under it. Rather than successive over relaxation,
Undershoot.
rather than SOR, what do you call this one? This successive under relaxation. And the factor that we multiply the progress with, it's actually less than 1. So in Fluent, for example, that CFD software that I'm using, you actually have this factor, and basically they would recommend use 0.7. So you are killing the solution rather than jumping the solution. You are killing it for certain situation. When the solution starts to oscillate, you basically say, no, I don't want to give you the whole thing. Let's slow down. Take your time and don't go there yet. Alright? Does this make sense? So we are talking about this much. We are talking about the difference between 2 iterations. Should we take that number, or should we basically make it bigger or make it smaller? Right? So how do you do that? So in that algorithm for Gauss-Seidel, right? When you think about it, we want to put our hands on the extra x, the amount that will be added to us. All right? So this formula over here, don't look at the red one yet. The formula over here, that's the formula for, right, for the x in u, right? That's not for the difference between x in u and x old. I want to see the difference between x in u and x old, so I can multiply by 1.5 and make it bigger. So to get it, you basically add x and you multiply x. Sorry, you add and subtract. So this is old and old. So what you did right now? What you did right now is suddenly now you have x in u is equal to x old plus everything else. So everything else, let me hang it in green. So this, now the formula is telling you x in u is x old plus something. Right? By adding x old to this, this now is the new improvement in x, how much x will change with. This is what get multiplied by 1.5 if you want to do over relaxation, or 0.75 if you want to do under relaxation. Right? So again, this is how when you look at the homework problem and you want to see, is it Jacobi or is it Gauss-Seidel or is it successive over relaxation or under relaxation? It's the formula that will be written there. Alright? Does this make sense?
So plus is over and minus is under.
You do either one or not both, like you have them written there.
Guys, the difference between over relaxation and under relaxation is not plus or minus. It is the coefficient. Are you making it bigger or making it smaller? You don't control, you don't change the amount of change that the method is giving you. If the method is telling you that x1 need to drop 0.7, you don't want to say, no, I'm going to increase it 0.7. No, it has to be minus 0.7. It's just that you want to make this minus 0.7 minus 0.8, or you want to make it minus 0.5. You want to magnify the signal or shrink the signal. Right?
So you have plus x minus x.
Right, which amount to nothing, right? If you add and you minus, you don't do anything.
Yeah. So you only
But
use one of
then
them.
in Gauss, no, you keep both of them. Right?
You change the coefficient.
You just, what you do is that you have this in Gauss, in SOR, you have this multiplied by alpha. So you will see the formula has x old plus this multiplied by alpha, where alpha is the successive over relaxation factor. Or it could also be successive under relaxation factor depending on its magnitude. So before the program starts, you will say alpha is 1.5 or alpha is 0.7 or 0.8. Then it's under relaxation, not over relaxation. Does this make sense? Right? You don't like it. Why? You don't seem to like it. What's wrong?
I'm not getting you're squiggly underneath the plus.
The which one? I don't see.
Like your green.
This?
Like you exclude the plus x to the j.
Right, because I want to write this formula as x new equal x old plus something. That something will represent the change in the x old. So I have to introduce x old and x new. See, if I multiply, let's forget about the red. If I just multiply this bracket by alpha, what did I do? He basically tell me, the method is telling me x new is 3. You are saying, no, it's not 3. It's 3 point, and then you multiply it by something. No, that's wrong. You're supposed only to multiply the increment in the x, not the whole x. Huh? It's as if you are basically multiplying the duck into a dinosaur. You're saying, it's a flying dinosaur. No, you're just multiplying the distance that the duck travel. It's the increment that the duck travel. You are thinking, next step, I think it will fly this much. Not that itself the duck will get bigger, then I can shoot easier. No, it's how much it will travel. How much will the x move? Right? So this is wrong. This is right. This should be multiplied by alpha. Okay? You can bring bunch of you can see how people write those successive relaxation program all the time. So let's talk about 24. So L conditioned system. We'll talk more next time, but for now let me just say that, see this two red guys, sorry, the two blue lines. This is a solution. Right? Those two blue lines again, let's delete the red so that you can see. They'll still have one solution, okay? But because the two systems are so close, the two equations are so close, the two equations almost look like each other. If you substitute with two different x here, I mean those are not the solution, right? Those are your version of the solution. This is what you get after 5 iteration. This is the actual solution. Those guys will basically give you a very small residual. When you try to come up with the R, A minus the B minus, sorry, the AX wiggly thing, you will end up getting with a small number. But it doesn't mean that X is a solution. It just means that the system is ill-conditioned. Right? So, we'll talk about this next time more. Right? But for now, you guys have any questions for me? We'll finish this next time. Yes? Right, so the plus, say, yeah, let me write this so that it's clear. So the new formula will look like this. Guys, listen. So I'm writing the formula for the successful relaxation method now. So it will look like this. Xj m plus 1 equal to 1 over Ajj Bj minus sigma, everything basically, I'm not gonna, minus sigma minus, and let's close this bracket, minus xjm, the whole thing is multiplied by alpha plus xjm. What's xjm? Those are the old. Let's make them blue, or let's just mark them. So old, and this is new. And S you are too. It's just the value of alpha that will decide. It's the same formula. Exactly. The whole thing is the same. The only difference. Say that again. So the xj, the xj itself, because we are this equation, this line is written just for xj or x5, for example. You are solving x5. You don't have a choice of using x5 in this formula, x5 old or new. You have to use the old because you're just calculating the new right now. It's those guys here that you have a choice between old or new. So are you asking in the SOR, do they use all the old ones or all the new mix? Right. Right. This is my xj new, x5 new. You feed it, and when you calculate x6, of course you use the new x1, the new x5 here. So it's Gauss-Seidel, meaning all the new variables are being used all the time, except that when we calculate the new variable, we give them an extra push. We just don't get what the formula gave it from Gauss-Seidel. No, we give them that push, that alpha. Sometimes the bush is bigger than 1. Sometimes the bush is actually not really a bush. We shrink them a little bit because we want to reduce their progress. More questions? All right. Thank you.